introduce our third speaker, Dominique Guillot from University of Delaware, who will talk about totally positive kernels, Polya frequency functions, and their transforms. Please.
All right. Thank you very much, everybody, for coming. And also thank you very much to the organizers for organizing this very nice focus program. Unfortunately, the schedule often conflicts with my teaching schedule, so I'm not often able to come to the live talks, but I'm trying to watch as many of the recordings as I can. So the work I'm going to talk about today is all joined with Alex Belton, Polya Kari, and Mihai Putinar. So I'd like to discuss composition operators that preserve the total non-negativity or the total positivity property. So since I'm not so sure most people are familiar with these notions, so I decided to split my talk into two parts. So in the first part, I'm going to focus on an overview of total positivity. And then after, I'll move to composition operators that preserve this property. Okay, so let's talk with total positivity. So first of all, if we have an m by n matrix with real entries, so we say it's totally non-negative, or Tn, if all its minors are non-negative. So really all the minors of all different sizes anywhere in the matrix. So in particular, the 1 by 1 minors, namely the entries, so they have to be non-negative, but also all the 2 by 2 minors anywhere, the 3 by 3 minors, and so on and so forth. So it's a very constraining property, if you want. In particular, if you have a matrix that is real symmetric and totally non-negative, then certainly it's positive semi-definite, right? Because the principal minors will be non-negative among all the other ones. The set of totally non-negative matrices is certainly closed if you rescale by a non-negative constant. It's also closed under the matrix product, as you can check using the Cauchy-Binet formula. In case you don't remember what that is, so the Cauchy-Binet formula tells you how to compute a minor of a matrix product. So you can always write that as a sum of products of minors of the two matrices, where you the sum in the middle index, if you want gamma, is over all the subsets of the appropriate dimension. So from there, it's very easy to see if you multiply two Tn matrices, the resulting matrix is certainly also going to be Tn. There are some related important notions. So totally positive matrices are those where the minors are strictly positive instead of only non-negative. And then we say a matrix is Tnk or Tpk if the minors of order at most k are either non-negative in the Tnk's or positive in the Tpk's. In case you're saying that for the first time, so maybe you're wondering, how am I going to check for this property, right? Because there are lots of minors that one needs to verify. And especially if you remember, for positive semi-definite matrices, we don't have to check all the principal minors. We can just check the leading ones. So maybe there's something similar for totally non-negative or totally positive matrices. And unfortunately, for totally non-negative matrices, not really, because if you pick any indices for a minor, like you pick the location of some minor, I claim I can build a matrix for which this particular minor will be negative, but all the other ones will be non-negative. So you really need to check all of them if you want to check for total non-negativity. That's the bad news. However, there are lots of relations between minors of matrices. This has been studied a lot in connection to cluster algebras. That there's been a lot of activity in that area in the past decades. And in particular, if you want to verify total positivity, so one can show you don't have to check all the minors. In fact, there's a collection of n square minors that is sufficient for checking, not any n square minors, but an appropriate collection. And one can show the bound n square is sharp, so you cannot do any better than that. So at least this is better than checking an exponential number of minors for total positivity. One just have to verify these n square minors. Now, more generally, if you have a kernel, so a function on x times y, where here x and y are totally ordered sets, I say it's totally non-negative if basically just like if you have a positive definite kernel. So whenever I form a matrix using the kernel, so you pick some points xi, you pick some points yj, and then you form this matrix k of xi, yj, I want it to be totally non-negative for any choice of the x's, any choice of the y's, and any n bigger or equal to 1. And here I want to point out that it's important that these sets x and y have some notion of order. So they need to be totally ordered because if not, if I swap the order of some of the points, this is going to affect some of the sign of some of the minors. So it's actually important that you have some way to order them for this notion to make sense. Okay, again, for those who are seeing that for the first time, you may feel like this sounds like something a bit artificial, this notion of total positivity, but I claim it arises in just so many areas, in almost any area of mathematics, actually. Some of the original motivation in analysis came from Polya, who was looking at the sign changes in coefficients of Taylor series. So what you can show is, let's say you take some vector and you read its coefficients from left to right, let's say, and you count how many sign changes do you see in that vector. So if you apply a totally non-negative matrix to that vector, the resulting vector will not have more sign changes. So because of that, we say that totally non-negative matrices are variation diminishing. And more generally, the totally non-negative matrices are exactly the matrices with that property. So those that reduce the number of sign changes. So that's one reason why they became popular in analysis around the 30s and the 40s. So they've been very well studied by Polya, by Schoenberg in connection to these kind of problems. Another really nice application that I like is in Gabor analysis. Some of you may have attended the talk by Yuri Lyubarsky in the interpolation and sampling session, where that connection was explained. But there are many other areas where this arises. Another important one is in the theory of splines that was developed by Schoenberg, where total positivity also plays a very important role. Okay, so what are some examples of totally positive kernels? I think one of the simplest that you can build is the Vandermonde kernel. So k of xy is x to the y, which I claim is TP on 0 infinity times r. So essentially, if you choose any collection of positive real numbers and any set of real powers that you order as usual, and you build this kind of generalized Vandermonde matrix, you can verify the determinant is always positive. As a result, we have an example of a TP kernel. Another important example that I believe was first studied by Polya is the Gaussian kernel, which is always totally positive on R2. As a matter of fact, I claim this example is a special case of the first one for the following reason. So if you form any finite matrix using the Gaussian kernel, you can show that it is in fact a rescaling of a Vandermonde, a generalized Vandermonde matrix using some diagonal matrices with positive entries. As a result, if you apply again the Cauchy-Binet formula, you can show that the determinant of these matrices are all positive, and therefore that the Gaussian kernel is totally positive. Okay, so the Gaussian kernel is actually a special case of a much more general construction. So just like we have positive definite functions, the analog, if you work with total positivity, is called a Polya frequency function. So these are kernels of the form f of x minus y. So these are like Toeplitz kernels, if you like. And usually to avoid some undesirable cases, we also assume the function f is Lebesgue integrable and that it's non-zero at 2 or more points. Now, amazingly, the functions f that yield totally non-negative kernels are very well known. They've been characterized by Schoenberg in the 50s. So we have the following results. So suppose f is a Polya frequency function. Then first of all, you can compute its bilateral Laplace transform. It's going to converge in some strip that contains the imaginary axis. And there, we know exactly what that function would look like. So if you look at 1 over the Laplace transform, let me call that function psi. So one can show this is an entire function that belongs to the so-called Laguerre-Polya class. So a function of the following form. So there's an exponential factor, and then a product of that form, where all the alpha j's, they are non-negative. So in other words, the zeros of that function are all real on the negative real axis. So any Polya frequency function yields a Laplace transform of the following form. But also conversely, if you start with a function in the Laguerre-Polya class, you look at 1 over psi, this is going to coincide with the Laplace transform of some Polya frequency function wherever both of them are defined. So there's really a correspondence between the Polya frequency functions and the Laguerre-Polya class. Another important construction is the following. So suppose you take a sequence AN of non-negative real numbers. Using that, I can build an infinite couplets matrix as follows. So the entry Mij is just simply Ai minus j. So you get a couplets matrix like that with zeros above the diagonal. Of course, you can also consider two-sided sequences if you want to fill up the upper part of the matrix. But here, let me just consider the one-sided version. And then whenever that matrix is totally non-negative, we call the sequence a Polya frequency sequence. And then once again, amazingly, the sequences that yield totally non-negative arrays, they've been characterized. This has been done by work by Eisen, Schoenberg, Whitney, and Erdrey, again in the 50s. And the characterization is as follows. So suppose this matrix X is totally non-negative. So what you do is you take that sequence and you use it to define the following power series. So just sum of an z to the n. So if m is totally non-negative, what you can show first is this function is actually going to define an analytic function on a neighborhood of the origin. And that function extends everywhere to a function of the following form. So you have some zeros maybe at the origin, an exponential factor, and then this product that gives you more zeros and some poles. And here, all the alpha j's and the beta j's, they are non-negative. So namely, meaning, so you have maybe some zeros at the origin, then all the other zeros are going to be on the negative real axis. All the poles are on the positive real axis. So basically, the zeros and poles, they're all real. On the one side, you have the zeros. On the other side, you have all the poles. And vice versa. So if you start with any function like that, you expand it in as a Taylor series, the resulting coefficients are going to yield a totally non-negative matrix. This is very, very surprising. How can one get such characterizations? So very often, the way we prove these kind of results is you first try to find as many examples as possible, like as many examples that work, and then hopefully you can prove that you found them all. And this is exactly what Eisen, Schoenberg, Whitney, and Erdrey did. And just to give you an idea how that works, I'd like to show you why any of these functions is going to yield a totally non-negative array. So it works as follows. So let me denote by MF the array that corresponds to the power series with coefficients an. So two simple observations. So first of all, if you multiply two of these arrays using the usual matrix product, it's not hard to verify that you get another array of that same form corresponding to the function f times g. So there's a correspondence between matrix product and just multiplying the two analytic functions. As a consequence of that, if the array has an inverse, that inverse needs to be the matrix corresponding to 1 over f. And now we proceed as follows. So first of all, you can look at f of z equals z, just to take care of this z to the k factor first. So if you look at f of z equals z, so that corresponds to the sequence 0, 1, 0, 0, 0, 0. Very simple exercise. You check this array is totally non-negative. Fine, no problem with that. Second example, if I take alpha non-negative, look at the sequence 1, alpha, 0, 0, and so on. Or in other words, look at the function 1 plus alpha z. Again, very simple exercise. You check, sure, that's totally non-negative. No problem with that. Okay, now third observation. If I multiply two Tn arrays, this is going to be Tn. This is again Cauchy-Binet at play here. As a consequence, if two functions generate a Tn array, their product is also going to work. So now we prove that several of these functions work immediately, right? Because the z to the k factor is okay. Then finite products with just the numerator here, the 1 plus alpha z, this is going to be fine. So now what about the denominator and the exponential factor? So how do we get those? So for the denominator, we have to observe the following. So if you take an invertible Tn matrix, if you invert it, usually it's not going to be totally non-negative. However, the so-called signless inverse is actually totally non-negative. So the inverse where you forget about the sign. So essentially you compute all the cofactors, but you don't put the additional sign in them. That's the signless inverse. So that's a classical result that this signless inverse is automatically totally non-negative. And if you think about it, if f of z generated the original matrix, when you take the signless inverse, the function that corresponds to that is not 1 over f, but 1 over f of minus z in order to remove the signs in the inverse. As a consequence of that, if f generates a pf sequence, 1 over f of minus z is going to do that as well. We knew that 1 plus alpha z was working. Therefore, 1 over 1 minus beta z will work as well for any beta non-negative. Okay, so we're almost there. So now, what if I take limits? This is also very easy. The determinant is continuous. So if you take a limit of Tn arrays, this is Tn. So therefore, we can go from a finite product to an infinite product. And now the only thing we're missing is this exponential factor. Why does this generate a Tn sequence? This is just the simple, observation that the exponential can be written as this limit. Now, if you look carefully inside the parentheses, this is a function of the form 1 plus alpha z. We know those work. You raise it to the power of n. Products are fine, so that works. Then you take a limit. That also works. So exponential is fine. And therefore, we've proved that every single of these functions is going to yield a totally non-negative array. The converse, of course, is much harder. You need to show the power series is actually convergent and that this is everything that you get. So that's a tricky part of the proof. Okay, so some applications now of these sequences. Suppose I consider a polynomial with, let's say, real coefficients. And let's just assume here that an is positive. Of course, it's very easy to observe if this polynomial only has real and negative roots, then all the coefficients will be non-negative, right? You just multiply all the linear factors, and then certainly all the coefficients will be non-negative. The converse, of course, is false, right? So, for example, if you just take the simplest example probably one can think of, you just look at 1 plus z squared. That has two complex roots, so the converse fails. So naturally, one may wonder, what is the correct converse? So what are the conditions on the coefficients of a polynomial in order to only have real negative roots? And it turns out we immediately know the answer using Polya frequency sequences, because suppose I take a sequence of coefficients that are non-negative, that's a necessary condition as we observed above, then all the zeros of the polynomial will be real and negative if and only if the sequence of coefficients that you add zeros at the end is a Polya frequency, right? Because if I go back to the characterizations, if I have a polynomial that only has real negative zeros, it's going to be a finite product of factors 1 plus alpha z, certainly. And therefore, by the characterization, the sequence of coefficients gives you a totally non-negative array. So what that means is, if I go back to the matrix we had, so if you write down the coefficients of your polynomial, and then you shift them every time you move to the next column, you compute all the minors of that matrix. The conditions that you get is exactly what you need to characterize the polynomials that have negative real roots. Isn't that incredible? This is actually quite complicated. You need lots of inequalities on the coefficients for that to happen. You may wonder, well, what if I actually want to have complex roots as well, but I would like to make sure the real part is negative? Then there's also a similar result. So these polynomials are usually called quasi-stable. So suppose now I take a polynomial. Notice here I wrote the coefficients in the reverse order to what I did before. There's a reason for that, you'll see in a minute. But let me assume these coefficients are all real. And let me assume the first and the last one are positive. So as I was saying, a polynomial is quasi-stable if all its zeros are in the closed left half plane in the complex plane. So in order to characterize these polynomials, we attach a different kind of matrix to P. So we build the so-called Hurwitz matrix associated to P. And then much more recently, so the result that I showed you before was from the 50s. But in 2012, it was showed by Holtz and Tyaglov that a polynomial P is quasi-stable if and only if that Hurwitz matrix is totally non-negative. So again, total non-negativity is used here in order to characterize the roots of polynomials. Okay, so that's all I wanted to say for now about total non-negativity. Hopefully, I'm convincing you that this is something worth looking at. This is something very useful and interesting. So now, what about composition operators? So here's the main problem I'm interested in. So suppose I take two totally ordered sets x and y, and I take a function f. I would like to know, when does composition by f on the left preserves total non-negativity, or similarly for total positivity? So in other words, given a function f, I define an operator cf, where cf of k will be f composed with k. When does that operator map tn kernels into tn kernels, or TP kernels into TP kernels? An example of why one would care about that is, let's say we want to study the stability of the Tn property. So suppose I take a Tn kernel K, and I raise it to a small power, let's say 1 plus epsilon for some small epsilon. Is the resulting kernel going to be totally non-negative? And of course, that corresponds to the case where f of x will be x to the 1 plus epsilon. Does that preserve total non-negativity? Another closely related problem is, what if we restrict the kernels to some natural families, like, for example, the Polya frequency functions, the Polya frequency sequence, and so on? Another example of applications of that will be, suppose I take a quasi-stable polynomial. I want to act on its coefficients, so I transform the coefficients. For example, you can take a power of the coefficients just like above. Is the polynomial resulting from that operation going to be also quasi-stable? And of course, this is equivalent to preserving total non-negativity on some special matrices. So here the Hurwitz matrices. Okay, so we were able to answer many of these questions. So let me start with the case where X and Y are some finite, totally ordered sets. So in that case, the problem is equivalent to the following. So suppose I have a function from R to R in some matrix A. I'm using the following notation. So F bracket A is going to denote the matrix that I get by applying the function F to the entries of A. So we would like to know, when does the operation that takes the matrix A, maps it to F of A, maintain the total non-negativity property or the total positivity property? And so we were able to completely answer that question. So suppose I have some function F, and suppose I look at M by N matrices, and let me denote by D the minimum of M and N. So we can show that the following is equivalent. So F preserves total non-negativity when applied entry-wise on M by N matrices, if and only if it preserves total non-negativity on D by D matrices. If you think about it, this is just completely trivial. So the only reason we get that is because, of course, if I have an M by N matrix, the only square minors I'm going to be able to form are going to be at most D by D, certainly. So these two equivalents are obvious. But now here comes the interesting part. So the only way this can happen is if either F is a non-negative constant, which obviously works, right? If you set all the entries to be a constant, this is totally non-negative, that's fine. Or the following happens, depending on the dimension D. So first of all, if you preserve total non-negativity on 1 by 1 matrices, this is absolutely obvious, there's just one entry. So in order to preserve non-negativity, you just need any function that's non-negative. Completely trivial. But as you increase the dimension, the property becomes more and more constraining. So in all cases, we can show the only functions that preserves total non-negativity are power functions. When d is equal to 2, any multiple of a power of a non-negative power works. And quickly, as we increase dimension, as soon as we hit dimension 4, the only functions that preserve total non-negativity are multiples of the identity. And that's it. So it's a very, very rigid property in some sense. So these are the only preservers, quite surprisingly. Okay, so a couple of remarks about that result. So we're not making any assumption about the smoothness of f. So we just start with an arbitrary function f, and then everything follows immediately from the total non-negativity property. We can also obtain a similar result if you only work with symmetric, totally non-negative matrices, the same result holds. And maybe just to comment a little bit about the proof. So how does one get such a result? So basically what you want to do is just choose some matrices cleverly. You apply the function to them, and you compute the determinant. And every time you do that, you get some kind of functional inequality about the function f. So the first thing you can do is you just take a matrix like x, y, y, x. Easily, you can show that this implies the function f, if it preserves total non-negativity, it needs to be increasing. So you already know it's increasing. An increasing function is measurable, so you get that it's measurable for free. If you pick the matrix again cleverly, you can show that preserving total non-negativity will imply the function f needs to be multiplicative. So now you know f needs to be multiplicative and measurable. And then using work, very classical work on the Cauchy functional equation, you can show the only possibility is f needs to be a power function. That doesn't give you the full characterization, but from there you can refine that analysis and just try to find out which powers are actually working. and find the exact result that we have here. So this is the approach that we used. Now, you may wonder, well, what about preservers of total positivity now? And thankfully for that, this is very simple, thanks to a result by Whitney from the 50s again, which shows that the TP matrices are dense in the set of Tn matrices. So that's not very surprising. However, this is not obvious at all if you think about it, because if I have a totally non-negative matrix, so all the minors are non-negative, how are you going to modify it to approximate it using a totally positive matrix? So in particular, you can't just add a multiple of the identity to it, just like you would do if you add a positive semi-definite matrix. You want to make it positive definite, then fine, you add plus epsilon times the identity, that does it. But now you need to take care of all the minors at the same time, so it's much more complicated. And Whitney found a very beautiful way of doing that in a constructive proof. And let me just briefly try to explain how this was done, because this is actually quite simple, but very interesting. So the proof goes as follows. So let's say we start with a totally non-negative square matrix that has rank R. So we do the following. So consider the matrix H defined as follows. If you look carefully, this is basically a Gaussian kernel in disguise here, just like we saw on the first slides. So if you use the Cauchy-Binet formula, you define the matrix HAH. So first of all, using Cauchy-Binet, it's certainly totally non-negative. But if you compute carefully using the fact that the rank of the matrix is R, you can find that all the R by R minors will be strictly positive. So the matrix is therefore TPR. And then as you let Q go to 0, it's very easy to see that the entries of that matrix U, they will converge to the entries of the matrix A. And therefore, you found a TP approximation if the original matrix was full rank. Now, what do you do if it's not full rank? So that doesn't quite work, but you can fix it very easily. So what you do is you first compute that matrix U. So you get something that's TPR, where R is the rank. And then all you need to do is you add Q to the 1,1 entry of U. And then what you can show is the matrix that you get by that process. So it's certainly still going to be Tn and TPR. That's not affecting that. We just modify the 1,1 entry. However, what you can show is by adding that entry, that increases the rank by 1. So we're not entirely done, but now you can see what's the next step, right? You just start reiterating that process. So you take that matrix V, you multiply by H on the left and on the right. Now it just became TPR plus 1. Add to the first entry, reapply the same process. And then after a finite number of steps, you're going to get a TP approximation. Letting Q go to 0 recovers the matrix. Therefore, that's it. That proves the density of TP in Tn. Okay, so therefore, because the TP matrices are dense in Tn, we just almost immediately obtain a characterization of the TP preservers now. So it just works as follows. So if F preserves TP matrices entry-wise, it's not hard to show F must be continuous. And therefore, using the density result of Whitney, F must also preserve Tn. And then from there is just a matter of adjusting a little bit the proof we had. We can immediately get the following characterization, which is basically the same thing that I showed you earlier, except with some minor adjustments. Like, for example, in the 1-by-1 case, you need to make sure the function is strictly positive, not just non-negative, because you want TP. There are also some cases like in D equals 2, alpha equals 0 is not going to work because that's going to yield the constant matrix. So we remove that. But basically, apart from that, the result hasn't changed. So we get the same characterization. So that completely solves the problem of characterizing the composition operators if the sets X and Y are finite. Now, from there, we immediately obtain a result for more general kernels when we preserve total non-negativity. So we have the following. So suppose X and Y are totally ordered sets of size at least 4. Then the composition operator K maps to F composed with K is going to preserve total non-negativity if and only if F is either a constant or a constant times X for some non-negative constant. And that, of course, just follows immediately from the finite dimensional result, right? Because all you can do is you take finite matrices and you can embed them as a kernel in some sense by padding with zeros, right? Like you define the function to match the entries of the matrix somewhere on some subset, and then you define it to be 0 everywhere else. And then the result just follows immediately from the finite dimensional result. However, if we try to go to TP now, the problem actually becomes significantly more difficult because now I can't just pad some matrices with zeros, right? Because I want the kernels to be totally positive, so I can't just put 0 entries. So in order to generalize that result, if we want to follow the same path as before with the density result, we need to know how to approximate Tn kernels using TP kernels. And as it turns out, this is a much more complicated problem that is still open. I'll say a few words about that just a little bit later. However, surprisingly, when we try to work on these problems, there's another bottleneck that immediately comes up, which is that for some totally ordered sets, there is actually no TP kernels that one can define on them. So in other words, some totally ordered sets do not support any TP kernel. So let me show you why. So suppose that the cardinality of the set X is bigger than the continuum. And suppose Y has at least 2 points. Now let me try to build a totally positive kernel on X times Y. Okay, so let me just choose 2 points in Y. Okay, so suppose this is some kind of representation of the kernel. So for each X and each Y, I need to choose some entry, right? Some K of XY for the kernel. So let's just focus on these 2 entries, Y1, Y2. And now remember the set X, we assume it's bigger than the continuum, bigger than the set of real numbers. So for every X, I need to choose at least 1 pair of real numbers to put here, right? Now, the cardinality of R square is the same as the cardinality of R during bijection. And for every X, I need to choose a pair of real numbers. But because X is so big, if you want, by some kind of pigeonhole principle, I'm going to run out of pairs of real numbers at some point. So in other words, 2 of the rows will have to be repeated at some point. As a consequence, if let's say these 2 rows are repeated at these 2 entries, the corresponding 2 by 2 minor is going to be 0, and therefore the kernel will not be TP. So that's a bit of a strange observation, but because of that, if the cardinality of at least one of the set is bigger than the continuum, there is no TP kernels on X times on Y. So this set is just empty. And therefore, the problem I'm asking for to characterize the composition operator is just trivial in that case. So that was quite surprising, at least to me, when we discovered that phenomenon that, in fact, we can't just work with arbitrary, totally ordered sets. But thankfully, we were able to quickly find a characterization of the totally ordered sets that do support TP kernels. So we have the following characterization. So suppose X and Y are non-empty totally ordered sets, then the following is equivalent. So first, there is a TP kernel on X times Y. So this is equivalent to being able to construct a TP2 kernel on X times Y. So in other words, if there is a TP2 kernel, that's okay. There's going to be a TP kernel somewhere. So that's fine. But the third part is the most important one. So either X or Y is a singleton, or there is an order preserving injection from X and Y into 0 infinity. So in other words, if you think about it, if we want to work on this problem, there's absolutely no loss in generality to assume that we take X and Y to be subsets of the real numbers, or even better, of the positive real axis. So that actually simplifies the problem quite a bit. So we don't really have to think about abstract totally ordered sets. Just any subsets of 0 infinity is going to do the trick. So, okay, so as a consequence, I'm only going to consider XY as subsets of 0 infinity in the rest of the talk. So now the question becomes, suppose I have a TP kernel on X times Y. Can I approximate it using, suppose I have a Tn kernel. Can I approximate it using TP kernel? And unfortunately, we were not able to resolve that question. It's still very open, and there's very little we know about that. However, at least we were able to obtain the following result. So suppose I have a TNP kernel on X times Y. Then I claim I can build a sequence of TP kernel that will converge locally uniformly at points of continuity in the interior of X times Y. And the proof of that result was obtained basically by generalizing Whitney's construction. So the first step, if you recall, that was this multiplication by this matrix H on left and right. And really, if you think about it, what Whitney is doing there is nothing less than a Gaussian convolution. So we first rephrased that operation as a Gaussian convolution. And then we try to mimic what Whitney was doing by adding one entry in some corner in some sense in order to increase the rank. Iterating that process, we can get a TPP approximation of any kernel. However, if you work with kernels, if you try to prove the convergent part, this actually becomes extremely challenging and much more difficult, but we were able to show at least some form of convergence. So that works. As a consequence of that result, so if I start with a Tn kernel, so it's going to be TP for any P. Well, it's going to be if I start with a Tn kernel, well, it's TNP for any P. That means I can build a TPP approximation. So for example, if your kernel is Tn, I'm going to be able to build an approximation for which, let's say, all the minors of dimensions at most 1 billion will all be positive. However, unfortunately, we just fall short of providing a TP approximation. So I cannot guarantee that all of them will be positive, unfortunately. So as I said, this is still a very open problem if some of you are interested to think about this. Okay, so therefore, our approach to try to use density fails to try to characterize preservers of total positivity. So we had to take a different route to be able to characterize the TP preservers. And thankfully, we were able to solve that problem for special families of kernels, and that was good enough to finish the characterizations. So more specifically, if we look at Toplet's kernels, so kernels of the form f of x minus y for some functions, then assuming the set x and y have some structure, so namely, if we assume x and y contain arbitrarily long arithmetic progressions that are equispaced, then we were able to characterize the preservers of these kernels. So we have the following result. So suppose x, y are subsets of the real numbers that contains arbitrarily long arithmetic progressions with the same step size, basically. So if I look at the composition operator on these kernels, then we can show the only functions that preserves the total positivity property are the multiples of the identity again. Now, as you can imagine, as a consequence, if I preserve total positivity for every kernel, in particular, we're going to preserve total positivity for these special kernels, and therefore the only functions that work will be multiples of the identity. Just as a corollary of that result, so if I take kernels on the integers, so we end up with the family of Polya frequency sequences that we discussed earlier. And as a special case of that theorem, we discovered that the only possible ways to preserve these the total positivity properties of these sequences is to operate with a multiple of the identity. So again, this is extremely rigid. There are not that many preservers except the trivial ones in some sense. Okay, so we obtained the following result. So if, again, we have a preserver of TP kernels, I'm sorry, it looks like here I inverted the F and the K, so it should be F composed with K, of course. Then the only preservers of total positivity are going to be multiple of the identities. And this is proved basically, by you start with your totally ordered sets X and Y, you can embed them into the real axis and basically use the previous result to conclude the proof. Okay, so in general, there are not that many preservers, right? So you may wonder, well, at least in some cases, do we get something more? And interestingly, the answer is yes. So what if instead of working with tuplets matrices or tuplets kernels, we go to Hankel kernels? So kernels of the form f of x plus y instead of x minus y. In that case, once again, we were able to obtain a characterization. And here the preservers of total non-negativity are exactly the power series with non-negative coefficients. So interestingly, in that case, we actually find lots of examples that preserve total non-negativity. Okay, so I'm almost at the end. So maybe just to conclude, a few open problems in case you're interested in this area. So the first one I already mentioned. If you take some subsets of the real numbers, are the totally positive kernels on x times y dense in the set of Tn kernels? Completely open. I showed you at least one partial results going into that direction, but we really have no idea. Like, are there more constraints that are needed on x and y? No idea. Even as a special case, what if I only care about the totally positive Polya frequency sequences? Are they dense in the set of all Polya frequency sequences? Even that is unknown. And perhaps a third problem that I think is very interesting, what if I only look at the Polya frequency sequences with only finitely many non-zero terms? So these are the ones that are generated by polynomials. What kind of functions preserve totally non-negative, total non-negativity, or total positivity on these sequences? If you think about it, this is equivalent to preserving real rooted polynomials with negative roots. And once again, just like the previous result I showed you, there are some non-trivial preservers in that case. Because, for example, by a theorem of Malo, you can show if you have a polynomial with real coefficients and all its roots are real and negative, if you take any integer power of the coefficients, the resulting polynomial also has this property, surprisingly. So there's definitely something interesting to be said, but we really have no idea what are the preservers in that case. So all the results I talked about are contained in this first paper, if you're interested. It's a little bit long, but there's really a lot of other results that, unfortunately, I don't have time to talk about. If you want more of a survey of these results, we just published an announcement paper, the second one, that contains also most of the results that I just discussed, and also a lot of other connections to other areas such as probability theory and representation theory. I leave you with a picture of our team on positivity pre-COVID, when we could still meet in person. Unfortunately, I haven't met my collaborators since that time. Hopefully that's going to change soon. So thank you very much for your attention. I stop here.
Thank you, Dominique. Questions, comments, suggestions? Well, if there are no questions, let's thank Dominique again. And this concludes our